What part of the Milky Way do we see? What can we make in orbit that we can't make on Earth? And are there different kinds of black holes? All this and more in this week's question show. It's time for the question show. Your questions, my answers. As always, wherever you are across my channel, if a question pops into your brain, just write it down. I'll gather them up and I'll answer them here. Another reminder that we have halved the size of the question shows and doubled the quantity. So there will be 2 question shows coming out this week, but they will be half the length. And that is like nicely snackable, just enough time to fall asleep to. All right, let's get into the questions. Finny Dale, when I look at the Milky Way, which part of the galaxy am I looking at? It really depends on which part of the Milky Way you're looking at. So we are embedded inside the Milky Way. You think of the Milky Way as this flat disk of stars. There's the central core that bulges up, and then there's just the disk that moves out to the outskirts. And the sun, the solar system, is about halfway between the center of the Milky Way and the outskirts of the Milky Way. We are embedded into the disk. And so when you go outside at night and you look up and you see the Milky Way, that view of the Milky Way changes from night to night, depending on where we are in our orbit around the sun. During the summertime in the northern hemisphere, we're able to see the core of the Milky Way. We see constellations like Sagittarius or Scorpio, and those are located near the core of the Milky Way. Think about the name of the black hole at the heart of the Milky Way. It's called Sagittarius A star. So it is this object at the, in Sagittarius, and Sagittarius is roughly the constellation that's at the middle of the Milky Way. And where I live in Canada, we can only see the core of the Milky Way during, say, June, July, August, and then it sort of fades out of view. Folks in Australia, they have a much better view to the core of the Milky Way, but we can't see it. And then over the course of the year, the Milky Way is always there. You imagine the Milky Way, right? And you imagine the core as sort of straight on. Then later on in the year, 3 months later, you're now looking off to the right. And then 3 months later than that, you're looking out of the Milky Way. You're looking through the remainder of the disk of the Milky Way out into intergalactic space. And then 3 months later, you're looking at another part of the Milky Way. And then when summer rolls around for us in the Northern Hemisphere, then the core of the Milky Way is visible again. And so you are seeing different parts. You're seeing the Milky Way from every single direction as we go through the year. Phantom Harlock 78. For potential new technologies that could benefit from zero gravity facilities, would staying in orbit be sufficient, or would it need to be far from a large celestial body? Yeah, so the question you're asking is being in free fall around the Earth the same as if you were far away from the gravity of anything and you were just floating in interplanetary space or interstellar space or intergalactic space? And sort of at the first approach, yes, that feeling is identical, that the feeling of being in free fall around a planet is essentially the same feeling that you would have if you were floating free, drifting in between, if you weren't experiencing any unbalanced force on you. And so think about what it means to be in orbit around the Earth. The gravity of the Earth is pulling you down. The outward force is pushing you out from your momentum around the planet. And those two forces are perfectly balanced. And so you experience no forces on you. And when you are free floating in space, drifting from galaxy to galaxy, well, then the amount of gravity that is pulling on you from any direction is negligible. And so you're not going to experience any unbalanced forces. And so, if there's a lot of ideas about the kinds of manufacturing that we could do in orbit. Probably the best idea is that you can manufacture optically pure fiber optic cables that have a better transmission of light than the kinds of stuff that we could spin out here on Earth. And this has been proven and demonstrated, and people have spun these optical cables and then brought them back down to Earth and proven that yes, indeed, they are more optically pure. They're better for transmitting data. But of course, you're going to be spending tens of millions of dollars to build the machines that are going to be able to produce this in space. And so is it really worth it? Like, how bad do you want optically pure fiber optic cables? Now, there are other ideas as well that, maybe there could be drug manufacturing in space, other things like that. And yeah, that it'll be there'll be no difference about whether you put it into orbit around the Earth or whether you were willing to move your factory out in between galaxies. But there are other experiments that have been proposed where we don't really know. There's ideas about whether or not you could measure the force of gravity at really, really precise levels. And then, yeah, the influence of different objects in the solar system is going to start to have an impact. There's the gravity that you're going to experience from the Earth. But if you're in free fall around the Earth, you're not in free fall around the moon. You may be in free fall around the sun, but that's going to change as you complete your orbits around the Earth. You're going to experience the influence of gravity from Jupiter. And so for the most sensitive experiments trying to measure this, they're going to have to deal with all of these gravity fields in the solar system. But if you just want to make optically pure fiber optic cables, yeah, low Earth orbit is perfectly fine. Master of the game. Are there different types of black holes? Not exactly. You can really only measure a black hole with two numbers. You can measure the mass of the black hole and you can measure the spin of the black hole. You might be able to measure the magnetic field of the black hole, but essentially that's all you've got. And so you can describe any black hole with just its mass and its spin. You don't know what it's made of. It's made of black hole. You don't know what are the particles that are contained inside of it. It's just made of black hole. And so really the only way to distinguish between different kinds of black holes is that mass and that spin. And as the mass of the black hole increases, then the size of the event horizon around the black hole also increases in size. So for example, you've heard about stellar mass black holes and supermassive black holes, and maybe there are primordial black holes with the mass of an asteroid, and maybe there's a black hole that's the size of an atom with, the mass of a mountain. Well, they're all the same thing, just different amounts of mass. And you can turn a stellar mass black hole into a supermassive black hole just by feeding it more material. Emmanuel Winterfor 6189. Instead of using adaptive optics to compensate for atmospheric distortion, couldn't you just record a high frame rate movie of the distorted image and undistort it using software? Feels like it would be much cheaper and potentially more precise. I love when people say, why don't they just? There's probably a good reason why they didn't just. So the traditional way that astronomers deal with atmospheric distortion is this technique called adaptive optics. And what they do is they fire a laser into the atmosphere. And that laser provides a reference point, an artificial star. And then they'll point the telescope at the thing they're trying to observe, but also get the artificial star in the region of the sky at the same time. And since they know the shape that the artificial star is supposed to be, a dot, then they can actually change the shape of the mirrors on the telescope using pistons to be able to adapt to the changing atmospheric conditions. And so if the star wobbles a little bit, they can change the shape of the mirror to turn that wobble back into a point. And it's assumed that if you're going to do that, then the object that you're looking at that is very close to the artificial star will also be brought back into focus and be stabilized. And with upcoming telescopes like the Extremely Large Telescope, they're going to have multiple reference stars. The thing looks like it's firing turbo lasers out into space. And so it's going to have multiple reference stars. And so it's going to be able to adapt the shape of the mirror to be able to keep all of those reference stars in focus at the same time. And so the idea that you're proposing actually is used by people who do astrophotography of planets here in the solar system. A lot of amateur astrophotographers will take video of the sun or the moon or of Saturn or Jupiter, Mars, and they'll just run their video camera attached to their telescope for like an hour. And then they will take this video file and they'll feed it into a software program that then grabs little bits and pieces from all of the different frames, throws out all the times when the picture of Jupiter was very blurry, and even grabs little bits and pieces from each frame of Jupiter and then Frankensteins it all together into this image that looks surprisingly clear. And I guarantee that when you look at pictures of Jupiter or Saturn or whatever, and they've been taken by amateur astronomers and you're really impressed, that was the technique that they were using. And so the question you're really asking is like, why can't we just do that? Instead of, having pistons that change the shape of the telescope, why can't we just there's that word, just record video and then turn that into a thing. Well, the problem is that the kinds of objects that astronomers are looking at with those big telescopes are very faint, that the length, the exposures that are required to be able to achieve and to be able to show off the kinds of images that we see, they're running the telescope, for an accumulated, sometimes hours, days sometimes, of data before they finally have all of the data that they require. And so imagine you were going to run video, but every frame of that video was not 1/30th of a second, 1/60th of a second, but every frame is an hour, right? Think about how much video you're going to need, and that you're going to get over the course of that 1 hour long exposure. You're going to get all of the blurring. It's all going to be averaged out, and you're not going to have anything that you can use. Telescopes just aren't fast enough to be able to record something that would be bright and visible at that rapid speed. And so the adaptive optics, it's genius, right? And how well it works and how well it's able to essentially remove the effect of the Earth's atmosphere. And that is the most effective way to provide clarity to ground-based telescopes and even space-based telescopes, even though they don't have atmosphere, but that's a whole other rabbit hole. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments, as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who has already subscribed, and welcome to our recent newcomers: Mike Gales, Pete Hall in Wisconsin, Dustin Dombrowski, Jim Meredith, Grimm, and Brian Brown, and all of our patrons. We couldn't do this without you. Sam Wilson: when we see faraway planets through James Webb, how do we know that what we're looking at is still there? Depending on how the light took to get us, it might not even be there anymore. The kinds of planets that James Webb is resolving are ones that are within a couple of hundred light years of Earth. I think, at the farthest, you're looking at planets that are maybe 2,000 light years away from the Earth, but mostly they are in the 100 to 500 light years away. And when you think about the fact that a planet can survive for billions of years, right? The Earth is 4.5 billion years old. If you went out 100 light years away and looked at Earth and you thought, we see this Earth, but I wonder, is that planet still there? Yeah, it's still there. It's only been 100 years. That's nothing. There's this quote that people say, when you look out into the sky and you see all those beautiful stars, well, just like your dreams, all those stars have died. And that's not true. All of the stars that you can see when you go outside are relatively close and but also very bright. And in many cases, those stars are maximum 300-400 light years away. You're seeing them just a few hundred years in the past. And so, like your dreams, those stars are still alive. David White: does NASA have any plans for a gravity tractor experiment on Apophis or any other near-Earth object? No. So a gravity tractor is a great idea, where if you want to try to move an asteroid and in a way that is very safe for the spacecraft that's going to move it, what you do is you go into orbit around the asteroid. And then you very slowly, very carefully, maybe with an ion engine, put out little amounts of thrust from your spacecraft. So you're trying to escape the asteroid. But the gravity of the spacecraft is attracting the asteroid. And so the asteroid gets pulled along by the gravity of the spacecraft. Now, the amount of gravity that the spacecraft is going to provide is insignificant, and yet, over time, as long as you have enough time to work with, it will start to add up. And if all you're hoping for is that over the course of 30 years down the road, you're going to change the orbit of an asteroid enough that would turn a hit into a miss, this gravity tractor is a really interesting idea. Now, there are no concrete plans to actually test this out. However, the OSIRIS-REx mission has been reclassified to be able to have a new sort of second mission, and that is that it's going to rendezvous with the asteroid Apophis, which was largely considered for the longest time. Apophis was the most potentially hazardous asteroid that we knew of. And so when Apophis comes by, OSIRIS-REx, this will be its final form, is going to meet up with Apophis and go into orbit around it. And then in this process, astronomers are going to be able to use all of the instruments on board OSIRIS-REx that it did such a great job of analyzing the asteroid Bennu. It's going to turn all of that scientific study onto Apophis. And then at the same time, astronomers from Earth are going to be tracking the movement of Apophis as it goes past the Earth in this very critical time with OSIRIS-REx with it, and then be able to sort of calculate and understand how an asteroid moves. And OSIRIS-REx will be watching the asteroid, seeing how the Earth's gravity changes its shape as it goes past the Earth. So, a gravity tractor is not in the works today, but having this spacecraft at Apophis is going to go a long way for us better understanding what it might take. It's kind of hard. NASA was so successful with the DART mission, right? Just slam a spacecraft into an asteroid and see what happens. Turns out it works really well. And so, I think that if we have any more potentially hazardous asteroids, they'll go with the let's just fire a spacecraft to smash into it and change its orbit that way. It's rain. Hey Fraser, I'm thinking of heading to Alaska next year to try and catch the Northern Lights. What months do I have the best chance of seeing them before solar maximum passes? So we are probably at solar maximum right now, and this is the time of the maximum activity on the sun, and that correlates to the maximum amount of the most regular auroras that we're going to see here on Earth. But on the shoulders of the solar maximum, it's still pretty good. For the last year or so, auroras have been getting better and better and better, and so it's expected that for the next year, the auroras are still going to be pretty good. And so, you've got a year to work with when you're going to plan out your trip to go and see some auroras. So the thing that's more important than that is amount of darkness. When you go to Alaska and you're there in the summertime, you only get a couple of hours of darkness every day. And then the rest of the time it is either sunlight or twilight. It's very eerie. If you've ever been like near the Arctic Circle or above the Arctic Circle, it's very unusual to be 3 a.m. and it's still light out, 4 a.m. and it's light out. That it never really gets dark. And so as unfortunate as it is, you want to pick a time to go to Alaska when you're going to get the most darkness. And that means you're going to want to go in the dead of winter, as close to the solstice as you can. And, this is why Iceland is such a compelling place to go to watch auroras. They are above the Arctic Circle. And yet, because they have this, the AMOC, they have this warm water that flows past Iceland, it doesn't actually get that cold in Iceland, even in the middle of winter. Like every time I've been to Iceland, it feels very familiar to my own part of Western Canada, which doesn't get very cold. And so, if you're in Alaska in the middle of winter, it can get pretty cold. So consider other places as well, like Iceland. But yeah, you should be targeting maximum darkness. Thomas Kluza, how do groups of photons travel together through so many light years and reach us to create any meaningful image of objects? I imagine they would encounter many obstacles. So every photon that you see has made an unimpeded journey from when it formed to when it arrived at your detector, in this case, your eyeballs. And there's nothing in between. Like when you go outside and you look up into the sky and you see a star, and the star is, 100 light years away, then those photons have been traveling for 100 years and they didn't hit any interstellar dust, and they didn't hit any particles in the atmosphere, and they didn't hit any planets. They just went straight from the star to your eyeballs. And that's fine. That's kind of mind-blowing. And yet when you sort of take that to its logical conclusion, when you're looking through your radio telescope at the microwave background of the universe, that light has been traveling for 13.8 billion years. It didn't run into any dust. It didn't run into any stars. It didn't get absorbed by a black hole. It is a continuous journey. Now it might have made a few weaves and wobbles thanks to various gravitational wells that it went past. It was distorted, but it has traveled unimpeded. And so some of the photons were lost in that journey, but every now and then one completes the entire journey and makes it to your eyeballs, or your radio telescope, or your visible light telescope, or your James Webb. I hope you enjoyed this question show. Now, just a reminder, we record this show live every Monday sometimes at 5 p.m. Pacific, but we also have other streams as well. So just check for when the upcoming events are happening in the calendar, and then you can either put your questions into the YouTube comments or just show up for the live stream. I'm going to talk about an appearance that I made on another show, but first I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew M. Gross, Barry Lake Roofing, David Giltonan, David Matz, Dennis Alberti, Dustin Cable, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Rohrbach, Spiderswap.io, Stephen Fowler Munley, and Vlad Shiplin, who support us at the Master of the Universe level. And all of our patrons, all your support means the universe to us. So I had a chance to go on another YouTube channel last week, and that is Doom Debates. And this is a channel that's run by Liren Shapira, and he generally is talking to people about sort of the nature of existential dread and threat from artificial intelligence, but often the topics of the Fermi paradox and the Great Filter, and whether artificial intelligence could become an explanation for the Fermi paradox comes up on his channel. And so I reached out and asked him if he wanted to talk about space stuff. So we spend some time talking about existential threat from artificial intelligence, which, you know, I am concerned. And then we spend a lot of the time just talking about grabby aliens and the Fermi paradox and all that kind of stuff. So if you want to hear sort of my perspective and just sort of have a nice explainer on this from someone who is very smart, Liren is really, really clever. And we had a really interesting conversation about that and the nature of the multiverse and all kinds of stuff. So definitely check out this conversation over at Doom Debates. All right, we'll see you next time.